Thank you very much for this opportunity.
Please. Did Bill take the clicker?
Oh, did it? Yes. I was going to control. In case you had a bad slide.
Thank you. So actually, I've been discussing this paper before at the AA meetings in Boston. That was January. And these were my conclusions from that discussion.
Oh, no.
So it says, I like this draft and believe it's important. And I hope to see a complete draft in the near future. So let's see how my conclusions were affected.
Who invited you?
So the motivation for this paper is that adaptive learning generates stylized facts, especially when you work with constant gain parameters. But constant gain least squares learning tends to be unstable. Often the projection facility is used, but that's an ad hoc way to control this instability. And this paper proposes a solution, the multivariate Walker learning. Okay, so there are two examples, new Keynesian model. And actually, this draft of the paper has a new example, the restricted perception equilibrium. That was recommended to me in January. So I was very happy to see that it included in the paper now. Okay, so that's great. So I will say a few general things, and then in particular say a few things about this new part of the paper that I didn't know about yet. So the main results is that the Walker estimation of var1 is stable and yields all eigenvalues inside the unit circle. That's, I think, the theorem that Bill showed. And then, as I understand it, this is still a conjecture that Walker learning is in a self-referential system satisfy the E-stability principle. So if I understand correctly, the proof is not there yet, and that's because it's difficult to, because of this initial state dependence.
Not immediately obvious anymore.
That's right, okay. So in a new Keynesian model for realistic values of the constant gain parameter, indeed, Walker learning yields stable Monte Carlo simulation results. Okay, so different, better results in that sense from the unstable results of least squares learning. And also in the new example that the restricted perception equilibrium, Walker learning works better in this sense than least squares learning. Okay, so here are my general comments. So to me, it's very natural to use this Walker learning because then you have a learning scheme that beliefs are stationary. The fact that the estimates are always inside the unit circle, the eigenvalues are always inside the unit circle, is that it means that you believe in a stationary process, and the learning mechanism is also always maps you into a stationary situation. The other thing is that it's nice that this learning is based on simple things, first and second sample moments. Okay, that also I think is an attractive feature. Now, also, I like the example of the restricted perception equilibrium, especially the focus on an AR2 forecasting rule. Okay, and I like that because actually that is what we saw in some of the experiments, learning to forecast experiments we have been doing in Amsterdam. I'll say more about that in a moment. And also, I think this is an important extension compared to the work I have been discussing with the work with Maizu, because you consider AR2 rules, and that gives you the possibility of complex eigenvalues. And so that gives you the possibility of oscillatory convergence. Okay, and that is something we have seen in the lab, and that is something that is not there if you have a specification with an AR1 rule, because then basically you only have monotonic convergence. Okay, so I like this extension to an AR2 rule, or higher order ARP. So this is a question I have. I couldn't figure out the example, the answer myself. So maybe you can say something about it. What is the relation with the behavioral learning equilibrium concept, even in the univariate case? Okay, so in the univariate case, does your Walker learning scheme, is it exactly the same as the sample autocorrelation, or are there some subtle differences. And in that respect, at first I thought you must have something different because the work with Maizu in the univariate case has the possibility of multiple equilibria. And that is something you don't seem to have in your setting, multiple equilibria. Multiple stable equilibria, actually, stable equilibria under learning. But then actually I thought that there may be an important difference in the specification you have and we have. And so this is the specification you had, but you didn't have this noise term here. This is an IED noise term. You only had the autocorrelated shocks. And actually in our paper, indeed, if you don't have this noise term, equilibrium is unique. Okay? If you have this noise term, equilibrium is not unique and you can have multiple stable equilibrium. Okay? So you might still have the same situation. And I just show you a plot. This plot comes out of our JET paper. So it shows, this is for an AR1 rule. So this is the autocorrelation coefficient of the AR1 rule. This is the implied autocorrelation coefficient of the actual law of motion. And so this is this function. And you see there are multiple equilibria. There's 1, 2, 3 equilibria here. This one is unstable under learning. This one is stable. This one is stable. So there is a very high persistence equilibrium, stable under learning. And there's also a low persistence equilibrium, also stable under learning. And that comes out of this extra noise term that we had in the equation. Okay, so question, can this happen under Walker learning? In the univariate, even in the univariate case, when you have this extra noise term. Okay. Then a few comments on the RPE example and the AR2 example. Okay. Now we have actually run experiments very simple to your setting with the AR2 rule, and we also had exactly the same coefficient of the beta coefficient 0.95, so that's the coefficient before expectations. But these were experiments actually without exogenous correlated shocks. Okay. But what we found there actually, we find coordination on AR2 rules there. And I wrote down 2 particular AR2 rules that we've really found a lot in the lab. One of them is a very simple trend following heuristic. You just take the last observation plus gamma times the last price change. Okay, this is clearly an AR2 rule, and what is interesting, the first coefficient is positive, the second coefficient is negative. Okay, so this is a trend following rule. Another rule, which is a sort of anchor and adjustment rule, is similar to this, but this anchor is more complicated here. Okay, it's more complicated. This term, the trend following term is the same. The anchor is more complicated. The anchor is an average of the mean price and the last observation. Okay, this is again a rule that we found in the lab. Okay, that we found as examples where coordination on this rule occurred. Now, what is interesting, if you look at the last couple of plots you showed about Walker learning in the AR2 example, figures 14, 15 in the paper, you have cases where you have this beta 0.95, okay, you have autocorrelated shocks 0.5 and 0.99, and the estimates of your coefficients, what is stable under learning, I mean, I couldn't see it, you didn't report the numbers in the paper, so I had to look at the figures, and it was a little bit difficult to read, but my estimates are 0.8 and minus 0.3. Okay, which would actually be, well, a kind of trend following rule, because you have one positive coefficient and you have one negative coefficient. And also for this case you have one positive coefficient and one negative coefficient. Okay. And also it might be interesting to look in your example of the AR2 coefficient to see how does equilibrium, stable equilibrium, depend on the coefficient of the autocorrelated shocks. Okay, and these 2 examples suggest that when you increase the autocorrelation in the shocks, that you get stronger trend following behavior in your group. Okay, so these were my conclusions in Boston. So here, oh, now it is. I like it even more. Now I'm going to be a little bit more cautious. I hope to see a computer somewhere in the future. Okay.
Okay, thanks very much, Cars.